Welcome everyone to the sixth tutorial, and today we will be talking about transformers and multi-head attention. Transformers is one of our architectures which is one of the breakthrough papers, you can say. Similar to ResNet, it had an enormous impact on the community, especially in research and NLP, and this is why it's very good to know how it is actually built up, how you can train the transformer, and I can promise you that you will see the transformer again in this master program at some point. If you take especially NLP2 or other NLP courses at UVA, you will revisit the transformer architecture. In this tutorial, however, we will not focus on transformers on NLP, but we will rather focus on the theory behind transformers and what transformers can do beyond NLP. This is because there are different courses in NLP at UVA, so if you're interested in them, just feel free to, of course, take them, and we don't want to take away anything for these courses. However, also in the assignment you see already language generation, and there's just so much more to transformers that we decided to stick here with the classical things behind transformer. In general, so this notebook will go a bit beyond the lecture. This is because it is so important, the transformer architecture, as to know it. The details here, of course, were not relevant for the exam. This is something that is really for you to know here and will help you with the other courses that come and be talking about transformers. Therefore, I will also focus here more on the theory and less probably on the coding. So the coding, you can also take a closer look if you want yourself. So at the beginning, we again just import our standard libraries. We have again a few pre-trained models we download. We will again use PyTorch Lightning here. So if you don't know what PyTorch Lightning is yet, please look at tutorial 5, at least the first part, where this is explained in more detail. We also linked here a couple of blog posts about transformer and attention. If after the tutorial you still feel like you want to know more about it, we can really recommend to look into those blog posts, which are often then more specific to NLP and the origins of the transformer architecture. To start with, what is attention? So you will have already seen what is attention in the lecture, and attention can be defined in multiple ways. The one we will use here is the following statement, which I put up here. The attention mechanism describes a weighted average of sequence elements with the weights dynamically computed based on an input query and the element's keys. So what does that mean? It means that we have, first of all, an input of elements. So these elements, you can imagine we have a sequence of words, and then each word represents here one element. Over these, we want to perform a weighted average. So we want to average the features of the words, but we don't want to give each word the same weight. This weight we want to give to each word in the average. This one will be computed on the fly, so basically depending on the features we have. This gives us a very powerful framework, which is referred to attention, and we will introduce here first some notation we will use. So usually in attention you have the following three inputs: a query, keys, and values. The query is basically a feature vector which describes what are we looking for when we perform the average. So for example, what do we want to attend to? This is where attention then comes from. Keys is then for each, so if we want to average over words, the keys would then describe what each word has to offer. So basically what is in each word, so that the query and the key can be compared and see if the key matches the query or not. And then finally the values are the feature vectors we actually want to average over. And we have then one value feature vector per sequence element, one key element per sequence element, and then usually one query. So the query is then independent here. Additionally to it, we have a score function, which basically then takes the key and the query and says whether they match or not. Usually that is a similarity metric like a dot product or a cosine similarity. Visually, we can represent it then as follows. So if we have, for example, the sentence, "I am eating an apple," and we want to perform attention over it, we have now always one key vector and one value vector for each word, and we have a query. For example, the query feature vector could represent what is someone eating, or what is the object in the sentence. And then the keys and the query should be matched here by, for example, a dot product. We have a softmax that we represented up here. And then with these values, these alphas which are calculated up here, so these are single scalar values for the full feature vector, and they then all sum to 1, right, because we have a softmax. And we multiply then these alphas with the value vectors to get one output feature vector. This is then what we do in attention. So for example, then if we say, what is this person eating in the query, then we should have a high attention rate, so this alpha 5 should be close to 1, while all the alphas are probably close to 0. However, note that it doesn't have to be 1 alpha is 1 and 0 for all of the others. This is dynamic, and therefore the network can also average multiple, if, for example, multiple things are important here. There are multiple different ways of doing attention, and the attention we will look at here is self-attention. So self-attention takes this idea of attention a bit further, namely that it applies one attention for each sequence element. So meaning we will have, for this sequence, for example, of 5 words, we will have 5 values, 5 keys, and 5 queries now. Why 5 queries? So basically we will have one query vector per word, and each word will look at all the other words in the sequence. And will take then a weighted average over those to get features for itself to update, for example, the features of a word. This is then called self-attention because the sequence pays attention to itself. So each word pays attention to the sequence. Therefore, we don't have attention from one part to another, but actually inside the sequence we do the attention. This is why it's called self-attention, and this is a basic fundamental part in the transformer architecture. After having now looked at what is attention, we can now take a closer look at how is attention exactly implemented in the transformer architecture or in self-attention. So as we said, we will have one query per word, one key per word, and one value per word. Each query will then always look at all the keys and all the values. And you can calculate it as the following attention mechanism. So this attention mechanism is called scaled dot product attention. Why that? Because we use as a score function the dot product between the query and the keys, which is this matrix operation. Scale, because we have here a scaling factor I will explain in a bit. We take then a softmax over it and then multiply that with the value vectors. So this is nothing else than this operation here, just in this sequence 5 times in parallel with different query vectors. And therefore we will get as output 5 output features, so one output feature per word in the sequence. In a computation graph, you can also visualize it as following. So you would have here a key and a query, you do a matrix multiplication, have a scaling and an optional masking. So masking means if you, for example, have paddings in your sequence, then you would not want to attend to padded symbols, right? So there you could intervene on the attention probabilities to set sum to 0, and then just do a matrix multiplication with V. The factor of 1 divided by dk is actually quite crucial in the transformer architecture. Why is that? So you see we do here dot product between query and key. And usually these query, key, and value vectors will be some features we generate inside the network. So often we have some feature vector for a word, and we will apply one linear layer to create a query out of it, a key out of it, and a value out of it. And this, in case you actually use the standard initialization techniques like K-Ming or Xavier, you can assume that the query and the key usually have an elements with a standard deviation of 1. And if you perform a matrix dot product of 2 vectors where each element has a standard deviation of 1, your standard deviation or your variance actually increases by a factor of dk, so the number, the dimension of the key and the query. So for example, 128 or so. And that you see if you do a softmax over such high standard deviations, you likely get already 1s and 0s after the initialization, and your model cannot optimize it. This is why we scale it down. so that the initial dot product which goes into the softmax has also a standard deviation of 1, or basically the one we had as input. We can write it down here as a function. It's basically just the computation graph we had above. So again, that is, I think, no new functions besides maybe masked fill. Masked fill is in PyTorch a function where you can take a tensor, say a mask, so if, for example, mask equals 0, so this is a Boolean tensor, and wherever this is true, we will fill this tensor with this very highly negative number, so that if we perform a softmax over it, it has no effect, so it basically is 0. We can run it, and below here we can also do a small test just to see. So if we have the queries, the keys, and the values, we get a attention matrix of the React A, because each query basically is performed 1 and gets 1 attention value per key. And this one is then used to create these values output vector. So if you're interested, you can just check it by hand at least once, so you get familiar with what is attention here. With gate product attention then is the basic element of a transformer architecture. However, we can take one step ahead. So you have seen now what if we already have query keys and values, how we do it. But the transformer architecture now needs to apply this attention somewhere in the architecture, right? So therefore, we assume we have an input, for example, of a sequence. So if we go back on our initial example, we would have now one feature vector representing I, one feature vector to represent M, and so on. We now take these feature vectors called X and apply a linear layer to create out of those the value, keys, and queries. So these linear layers basically represent that here. So for each word, we basically just use a linear layer to create that. Afterwards, we apply a scale dot product attention, and therefore we get our output for attention. However, there's now a small trick. So you see this layer is called multi-head attention. What do we mean with multi-head? Well, namely that we apply multiple attentions in parallel. So instead of having one attention, we actually have multiple heads. So it is represented here in this picture that you not apply one linear layer to create one value vector for each word. You actually apply multiple linear layers to create multiple value vectors per word. And then we also apply these attention mechanisms in parallel and independently. So we will have each attention mechanisms on the same input instead of just having one. What is the advantage? The advantage is that the model can attend to multiple different things at the same time. So you can imagine if we look at a sentence like, for example, I'm eating an apple, then there might be also two queries like, what are you eating and what are you doing it all? So for example, what are you doing it with and what are you doing? These would be two queries. And if we have one head, the attention mechanism can only average over both eating and apple. Well, if we have two heads, we can attend for one head at eating and one head at apple and have then basically the feature vectors concatenated. So the first part of the feature vector, output feature vector, will represent apple, the other one eating. And this is then much better than having one big feature vector averaging over both, because then you can distinguish anymore where the features actually came from. So this is the whole idea behind multi-head attention, that you just apply multiple attention mechanisms in parallel, concatenate the output of all of those, and apply one final linear layer. Implemented, it's below here. So again, I don't focus too much in the coding today, but it's rather simple. So you have basically, you can combine all these linear layers down here to one linear layer, because this is much more efficient to actually run it in one linear layer. For example, the same is kind of in the LSTM that you can combine all the gate weight matrices, which is then more efficient to run because they all have the same input. And then we have one final linear layer for this one. And then you see we just generate the key, query, and value vectors, apply the attention all in parallel, and then return. The attention mechanism is popular for multiple reasons, and we will look at some of them. So one of them is that it is actually permutation equivariant. What does that mean? So if I actually shuffle my words in a sequence, then the output is also just shuffled, but it will be the exact same features. So if I, for example, take my sentence, I am eating an apple, and say apple eating I am n, so just mix up the words, and will apply then the layer, I will get exactly the same feature vectors as with the original ordering, however, just with new ordering also in the output features. Why is that? Well, because attention has no sense of ordering, because all elements are always looked at equally in the sequence. This has a very big advantage, namely that we have multiple, what is called here, we have a maximum path length of 1, so that if we do the gradient backpropagation, then you can see that we actually have no problems in RNNs, like applying a lot of layers after each other to backpropagate from the last time step to the first, because for a transformer, these two have the same distance f as the first and the second word in the sequence. However, the disadvantage is that the self-attention scales with the sequence length quadratically. So if we have a vector, a sequence length of 10, and compared to the computational complexity of 20, we actually have 4 times higher complexity, because we have to compare each word with each other. Right? When recurrency, we will have a linear increase. That's why, however, the self-attention has a big advantage. We can do parallel computation, so we can apply everything in parallel, while in recurrency, we'd have to take one step by a time, because we have to apply all these layers sequentially. Right? This is why it is often faster to run a transformer than actually RNN. All through the RNN has less operations overall.